And then, okay. All right, sorry. So all of the code that I'm going to be going through today is posted to Canvas in the files folder in notes. And I can't remember what I ended up calling it. I think they're reasonably well named. But like I said last time, what we're doing is we're going to introduce you guys to Vivado and VHDL, where Vivado is the design environment that we're going to use. So what I'm going to do is take you through making a whole project in Vivado. This is recorded and on my YouTube channel that you can find whenever I send out the recorded lecture videos. I have another kind of introduction to VHDL walkthrough as well. And you can find a bunch on the internet, but this is kind of direct for our class. So the first thing that I kind of wanted to go through is, a slide walkthrough just real quick of what I've provided for you as far as installing Vivado on your own. And I'm just going to pull that up and kind of walk through real quick. Let's see. So it should be in labs and then lab 0. I'll go ahead and download that. So you guys can go download this. It should be available. So Vivado, I have to change this, don't I? Stop sharing. Okay, so it's just a series of slides that is going to walk you through how to do it. Some of these are more important than others. So like in this one here, you can see that I have the SOCs and ultrascales unchecked. That's just to save room, because if you look down here, that's 25 gigabytes worth of install, even without those other ones installed. It's a large program. I guess disk space required, yeah, 24 gigabytes is what it told me when I installed mine. When it's installed, you're going to see Vivado HLS and Vivado. You're going to get really confused if you launch the HLS. Don't do that one. Launch Vivado. And then the rest of this is walking you through creating a project, but I'm actually just going to do that here in class. So Vivado, when you launch it, will look something like this. If it doesn't, you launched HLS and you're going to be confused. To create a new project, so a project is just going to be a grouping of files that it kind of keeps track of where they are in relation to each other. So you do file, project, new, and it's going to create kind of this walkthrough for you on how to set up your project. So I'm just going to click next. I'm going to name this one ECE 2700 intro, and I'm going to call it 2 because I have one already called just intro. Oh, intor. Wow, that's going to get confusing. Hello, typos. Okay, you want an RTL project always for this class. You're not going to be using any of the other like post synthesis. You won't do it. Now, you can add sources here if you already have files that you want to add. So like if you were to design a multiplier, you wouldn't have to create it every time. You could just import a copy of it or the original and just use it in a new project. I'm not going to do any importing, but what you want is to make sure that down here, this target language, let me turn on the annotation so I can doodle. Here, it says VHDL. That's what we want. We don't want Verilog. Verilog is the other language that we won't be using. All right. So I don't need any of that. Constraints are, it's a file that you'll learn how to make later. We won't use it for a while. It just tells the hardware that you're targeting how to interact with the software, the code that you wrote. basically. It's a link between what you write and the actual physical hardware. Parts. Generally, you're not going to care about the part in this class. The one that you'll be using in 3610, and we might get to touch it a little bit, oops, I launched it, is called the Basis 3. Now, the Basis 3 is kind of what's called an FPGA development board. The development boards are really useful because it gives you a bunch of what we call I/O ports or inputs and outputs, and it also has a few other, like it has built-in LEDs and built-in switches and the like. You'll actually get to see one of these later in the semester, probably. And they only cost about $140, which for some people is a lot. That's understandable. But if you're kind of into hobbyist activities in electrical engineering, this is one that I recommend. This is the one I chose to buy for this class. It's really quite nice. So I'm going to select that one, and then I'll just click finish. Okay. It takes a little while. It's not always fast. So this is more or less what your Vivado will look like when it's first launched. I say more or less because I've grown the scale so the text is easily readable for you. Everything looks really crammed because of that. So one of the first things that I like to point out to people is this project flow navigator window really walks you through the whole design. So you can set up your project in the project manager. IP integrator. So IP, you're going to hear IP cores a lot. An IP core is something provided to you that allows you to use someone else's code to implement a function. So like you don't want to write a USB interface. That's really complicated. They provide one for you. You would bring that in as an IP core. Then there's simulation, which we've talked about a little bit and we'll actually go through the day. There's RTL analysis, that's real-time analysis. Synthesis, implementation, program, and debug. Those are steps that we'll get more into later, but it's literally just go down this flow navigator and you'll end up with the right final project. Okay, here in this window, we have the sources window. So the sources window is where you're going to keep track of your files and what we call the file hierarchy. What file hierarchy means is if I have, I'll just doodle here, what we'll call the top file. So the top file is something that we'll make today as well. And it's what tells all the other modules how they're connected. So let's think about that example that we went through a couple days ago. Well, similar, right? So I say I have a mux. And this is actually what we're going to make. So it's going to have something like an adder and a subtractor and a mux all in one top file. It's going to tell them what ports are connected to which other ports. And the hierarchy in sources will actually display what goes underneath what. It's like your file browser, right? Where if you open up one and then the next and then the next, it's kind of a cascade of files. The hierarchy work here the same way. Okay, then we have the project summary. You're not going to worry too much about that one. Down here, though, at the bottom is a lot of useful stuff. The TCL console and messages and logs especially. This is where all of your error information is going to pop up. And I'll actually generate some errors kind of on purpose as we go through, and I'm sure I'll generate several on accident as well. Okay, so this is what Vivado more or less looks like when you see it. We want to add a source because we can't do anything without a source. And what I'm going to start off with, so I hit the, sorry, I'll point that out more clearly. This plus button is add source. You can also, under project manager, click add source. So I want a design source for now. Now, here, I don't have any files I could import, so I'll create a file. And we're just going to call this What am I going to call it? I'm going to call it mux. We'll just call this one mux. Why not? Okay, then I can click finish. This window then will always pop up. You can start entering your ports here. I don't tend to use it, so I just click OK and move on to the next one. Now what that has done is created in the design sources, under the sources menu, the mux. If I double click on that, it'll open up over here, and I'm going to go ahead and make that big. At the top, it will start off with a bunch of commented out code for you. So comments are noted by this dash dash. A comment means it's just for the humans to read. The machine will just completely ignore it, and it provides information. What it does at the top, what it's done here at the top is the typical thing that you do at a company where you'd write who you're working for, your name so they know who to contact if you screw it up, what it is, and so on and so forth. I start out in this class by deleting all of that because we're not working for a company and it's a lot of stuff. Okay, this next one, it says uncomment the following library declaration if using arithmetic function with signed or unsigned values. Okay, so we'll get to types later, right? So we talked about bits last time. Signed and unsigned is just the ability to write 100 or minus 100. It doesn't intrinsically have that. This library gives it that ability. So I'm going to do this, and I can now use that library. I always recommend using this numeric standard library. It is very useful. We don't need any of this comment yet, so I'm just getting rid of it. And then I'm going to uncomment port. So this is your bare bones VHDL here. You'll notice some things that I talked about last time, right? Here's that entity that I mentioned. Here's the architecture. Here they default call it behavioral. Sure, that's fine. Doesn't really matter what the name is. And it says of mux, that has to be the same as this entity. Okay, so it needs ports. This is the inputs and the outputs. This is the only thing that the outside world knows exists. So in a mux, I'm going to have an A, a B, and a select cell. Then I do colon and say what type it or mode it's in. These are all going to be inputs of type. And now last time I used bit. What I'm going to actually change up and use is standard logic. So standard logic is like a bit in that it has 0 and 1, but it has additional values as well that it can be that are useful in the real world. For example, it can be undefined. It can have a U on it, U for undefined. It can be Z, which is high impedance, which just means it's not outputting anything. It will accept whatever's coming in. And has several other values that we'll go through later. Just keep in mind, standard logic is easier to work with than bit. And it's enabled by that numeric standard library. Okay. Next, I need the output. We'll just call it C. It's an out. And it is also going to be standard logic. Okay, now notice the formatting. The first line I end with a semicolon. The second line, because there's not a new line, just ends with that parentheses to close off the port parentheses and ends with a semicolon. Okay, then I say end mux. Now I have to go start worrying about the architecture. Under the architecture, it has that begin. Under the begin, I'm going to go ahead and write the expression for a mux. And we talked about this last time. And all I have to do is say C, which is the output, gets assigned to, right? It's like equals to, but it's slightly, it's that less than, or yeah, less than or equal to symbol. And then I say something like A and not cell, or B and let me get this right and then I'll start talking. Okay, So it's A and not cell, or B and cell. That was the equation for a mux that we came up with last time. Boom, done. I've made a mux, except for I want to tab this in right just to keep the formatting clean and clear and easy to read. You'll notice if I do something like delete that semicolon, it has an error. The line after end behavioral gets this squiggly line underneath it. And that error says syntax error near end. But you'll notice that the actual error is the line before that. It's missing its semicolon. So when you start seeing errors, always check what's coming right before it to see if that's what's causing your problem. It is. Okay, no errors. I've made a mux. Now, I want to use this as an opportunity to show you that there's a bunch of different ways to do all sorts of designs, and they're not wrong. So let's go ahead and add a new source. Same thing, file type is VHDL. This one is just going to be mux, and I'm going to call this underscore bitwise. So something to be careful of in VHDL and most engineering software is they tend to not like spaces in your file or folder names. If the place that you save your files to or your file names have spaces in them in Vivado, they will not work. They will crash Vivado, and sometimes it will crash Vivado so bad you have to reinstall it. Yes, no, Vivado, engineering software in general has issues because they're not designed for mass distribution. It's a fewer number of users, and they assume that you are technically competent, which is not always a good assumption.
So is it just using like the Unix style file name rules?
Pretty much, yes. Yeah. And file names can also start with any letter. They hate starting with a number. That will also cause you big issues. So don't start with a number. Okay. So I don't see any way to open that up here. I created it right. Over here on the left, you can see sources. I just click on that. You guys can see my mouse, right? Yeah, good. Okay. Mux bitwise. I can double click on that. It's now opened up. And I'm just going to go through that same process that I did before, where I'm just going to delete some of this stuff. Uncomment that numeric standard. Uncomment the ports. Okay, that's all. Now there's going to be one issue if you were just to copy. There's a discrepancy between this and the code online. In the code online, I just called it mux again because I just built it multiple times. This is mux underscore bitwise. You want the name of it, so the entity name, to match the file name. It is actually a little bit forgiving about that sometimes, but I highly recommend following that method where your file name is the entity name. Okay, so what I mean by bitwise is, what if we want a 2-bit mux, meaning A and B each have 2 bits in them and C has 2 bits. So we're not just passing through 1 bit, we're passing through 2. Well, let's go ahead and use A, B as inputs again. And they're going to be standard logic, but instead of just standard logic, it's standard logic vector. So standard logic vector just means it's a vector of standard logic. It has multiple in it. Then we have to say how big it is. And the notation for that is, say, if we want 2 bits, I say 1 down to 0. Okay, 1 down to 0, down to being one word. The reason we do that is because it's saying left to right. And it's saying now, if I say 1 down to, I have the most significant bit, the largest digit, is on the left side of things instead of the right side. Okay, then I need select still. It's also going to be an input, but it's only standard logic because I'm selecting these together. Then I need the output, C out standard logic vector 1 down to 0. Okay. Remembering that VHDL is 0 index, that's why it's 1 down to 0 for a 2-bit vector. I think I may have made a 5-bit mux in the example code though. Okay, so now with this one, I can simply go ahead and say 1 bit at a time. So C at 0 is how I say this out loud. So C is a vector, it has multiple locations. The first bit of it gets assigned to, well, it's really just this equation, right? It's the same thing. So I'm going to go copy and paste that. With the difference being I need to specify that I want to take A at 0 and B at 0. So I'm concerning myself with just the first bit. I can then copy and paste that whole thing and substitute the 1 in for the 0. And now I've created C at 0 and C at 1 assigned to their values based on what the mux is doing. Right, so based on select, I either take the 2 bits of A or I take the 2 bits of B that I'm interested in. Are we lost? We're good? Okay. Now, you can imagine if you were trying to do an 8-bit mux or a 5-bit mux even, it gets repetitive. That's why I did the 5-bit in the example online, is because it would be a lot of copying and pasting. So we don't necessarily want to do that. So one of the things that we could do is we can start to change the way we handle the array. So select is just standard logic, right? If I want to do an AND operation of vectors of different sizes, it causes a problem. So ANDing a vector and a bit is problematic. So what you can do is there's this nice little code that you can use where I'm going to call it select array. And I'm just going to repeat select 2 times. Now, this throws an error. If I mouse over it, it tells me error near cell array. Well, that's because I put it in the wrong spot. But it's still going to have an error. Cell array is not declared. So C and cell are both declared as ports. If I don't want it to be a port, if I wanted an internal signal, then after the architecture, but before the begin, I type signal to tell it it's an internal signal, and I want it to be named cell array. Sorry, let me make sure I do all this correct. And its type is standard logic vector of 1 down to 0. Now I can use a select array. Ampersand, the and sign, okay? It is concatenation. What that means is it's taking one copy of select and another copy of select and sticking them together in one vector. The ampersand is not and the logical operator, it is and the concatenation. Don't confuse these. Concatenation is helpful. Okay, so I've made a select array out of selects. It's just duplicated. And now I can say something like C is equal to A and not cell array, or B and cell array. Now, if I had tried to do this with just cell, right? We see the little squiggly error bar underneath if I mouse over. Error type near cell, current type standard logic, expected type standard logic vector. Now it's just doing its best to guess which way you meant to do it. It may actually flip it. It may say, it may think that A is the problem rather than cell, right? And it would tell you opposite, but this is telling you a type error. They don't like being different. So that's why I created that cell array. Okay. So now this is another way that you can build a mux. Works just fine. But there's another way we can build a mux. I'm going to go ahead and build up. I'll create a new one for this one, actually. Again, add source. Next, create file. Mux underscore process. Again, I open up sources over here. Double click on the mux process that I just created. Delete the comments that I don't, well, I guess I'll just minimize that one maybe, huh? Delete the comments that I don't want. Uncomment the library. Okay. Again, I'm just gonna go still these ports because I don't want to type that all out again. There we go. Okay, so this next one is really going to be your introduction to what we call if statements. Now, if you've done programming, you've done if statements, right? And an if statement is just saying, if a condition is true, then do something about it, right? So it's like saying, if the light switches up, then turn the light on, right? So let's go ahead and kind of do that, which is to say that I need to do this in what we call a process. So a process changes things from sequential logic, from combinational logic to sequential logic. So sequential means this happens, then this happens, then this happens. So process. Now what the process needs, and we'll get more into details later, but it needs what we call a sensitivity list, meaning when do I execute this process? When do I evaluate it? Well, I want to do it on any of the inputs. So A, B, or select. If any of those changes, execute the process. Oh, and again, I'm going to tab this in for code clarity. Now, I like to just jump down and type end process immediately because I'm going to need that end process. Because I have a begin, I need an end. I don't want to forget it because missing ends gets really confusing. Okay, so then that process, I'm going to write my if statement. And they're really easy in VHDL, which I appreciate. It just says if cell is equal to, notice this is actually equal. This is the comparison. It's asking the question, is select equal to 0? So notice I have the apostrophes around it, or ticks, as you'll sometimes say, you hear me say, because tick is a shorter word than apostrophe. So it has the apostrophes around the 0 to let it know that that 0 is a bit type. It's a notation saying this is a bit, apostrophe. If you want a bit vector, it's quotation marks, which we'll see in a moment. Okay, then I say, then I want to do something with it, right? C is equal to A. Rather, C gets assigned to. Otherwise, else is the term for that. If select is not 0, then C is equal, or gets assigned to B. Now I need an and if. You'll notice the if doesn't have a begin, but it still needs the end if. Right? This is an if statement in VHDL. They're really easy. You can also have else ifs. So if you need multiple choices, right? So if this light switches on, or then turn the light on, else if this light switches on, then turn the light on, else the light is off, right? if, else if, else, and if is the general structure for that. This works. This will be just fine. Now, sometimes we forget that we need to be in a process. You're going to get errors. And if I mouse over this, it just says syntax error near if. It's not very helpful, right? So we have to be careful to remember to do our syntax right, because some of these errors are really vague and it can be problematic. Later, I'll give you more effective debugging tools than we start out with, but that's something to keep in mind. Okay, but there is a different way to do ifs. The ifs get kind of repetitive, especially if they're really big, and we will be using some fairly large, many optioned if statements. So what we do instead of the if is we use something called a case statement. And it's still basically an if statement, but it's just, what is the case of something? So let's case on select cell. Case cell is, and then I say when 0. So all this is saying is when select is 0. Oh, you don't use the N, you use that arrow. Okay. So when select is 0, then I'm going to say C gets assigned to A. When it's 1, then C gets assigned to B. And now there's this little issue where it wants to know what happens if that's not the case. Now we think, well, of course it's going to be 1 or 0, right? Because it's a bit, except for it's not. Select is standard logic. And because it's standard logic, it could also be Z or U, like I just talked. It could be something other than 0 or 1. So therefore, I need this when others. Sorry, I always forget this syntax. And I'm going to say it gets assigned to Z. Okay, so here's an error. Again, it's a type error because C is not a standard logic. It's not 1 bit, it's a vector. So instead of the ticks, I use apostrophes, or sorry, quotes, and then I use 2 Z's. Now it's happy. This green up in the top right near the scroll bar says that I have no errors. Yeah, you can actually mouse over. 0 errors, 0 warning, 0 notes. All's good. This code is clean and happy. Okay. Do we have any questions so far about what I've covered to this point? Feeling okay? Okay. Now, I'm going to go ahead and create another source. Getting the feeling that I'm going to be doing a lot of this, right? Okay. This one, I'm just going to call an adder. We're going to make addition. So later on in this class, you guys are going to build a circuit that's an adder. I'm going to do this the quick and easy way. This adder, I can change the port names. So we'll call it number 1, N1, N2. Those are inputs of type standard logic vector. I'm not the world's fastest typer, I apologize. Okay, so what this will do is take numbers N1, N2, and output a sum, right? Really easy, nothing complicated. Remembering that VHDL isn't sensitive to case. It's not case sensitive, but I try and do ins and outs in caps as well as the logical operations just to be clear. And then because I'm using standard logic vectors, if I was using like a bit vector, which also exists, I couldn't do this. But standard logic vectors let me do the following, where I say sum, and I would like to be able to do something like this. But you'll notice that's going to throw an error where it says 0 definitions of operator plus cannot determine exact overloaded matching definition for plus. What that's saying is, I don't know how to do this. You've told me to add 2 things that I don't know how to add. And that's because it doesn't actually add standard logic vectors. What you do instead is you need to do what's called a type conversion, is we can change it to something else. So what we're going to do is we're going to add, sorry, I always forget. Yes, this works. To unsigned numbers together. That is allowed, but you'll notice still an error because it's still going, I don't know how to put these 2 numbers into sum because it's, again, type mismatch. So what we want to do is we'll just turn them back to standard logic vectors. Now it's happy, no red bar. So this is your introduction to type conversion. If you need to add numbers together like this, turn them into unsigned, or you can even create them as unsigned signals, right? I could say something like, again, this is after the architecture, but before it's begin, I type signal, we'll call it N unsigned of type unsigned. Did I forget anything in that signal declaration? Sorry, some of this stuff that I usually would do, I'm cutting out just to keep it simple. I think we're okay. All right, so then I would have a signal N unsigned and I could operate on that instead of operating on standard logic vectors. Okay, so that's type conversion. This is something else you'll be doing a fair amount of. But I have an adder. Let's go ahead and create, just real quick, something similar. I'm going to copy all of this code. And create a new file. And I'm going to build a subtractor. The reason I just wanted to copy all of that is because most of it's the same. But I have to go in and change this adder to subtractor, and then I can just copy and paste it. You'll notice something handy in this design environment. If I double click, it highlights all other instances of that variable. So they're easier to find. Okay, and instead of sum, it's a diff. Change this sum. Come on. to a difference, and I change the plus sign to a minus sign. Nothing really special there, right? Just build a subtractor off the model of the adder. Now, you'll recall that I talked about that top file. So what I want to build now is a module that can either add or subtract depending on the input called select, essentially, right? That mux is going to choose whether I'm adding or subtracting. So another way of doing it, I'll go ahead and draw so you don't have to picture it in your head, is I have a top file. I've built a mux. I've built an adder, subtractor. They're connected to the mux. And depending what select is doing, we're either going to put the output C as the addition or the subtraction. So we're always calculating both the addition and the subtraction. We're just choosing which one comes out, right? And each one of these has A and B attached to it as inputs. So this is what we're building. This is kind of my horrible drawing of the ultimate top file that I'm trying to build. Okay. I need to make that top file. So let's go ahead and add a source. Now, a lot of times, what I would do is if it is my real genuine top file, I would just call it top. But maybe I want to use this kind of thing in a larger design, which is a lot of what you're going to be doing. So I'm not going to call it top. I'm going to call it add or subtract. Long name, but it communicates what it's doing. It's better to be clear than vague when naming your variables, even if they're longer. Okay. Now, we now have add or subtract. I know I want this to be my top file. How does it know it's supposed to be my top file? Well, see this little icon next to mux? That icon means currently my mux is my top file. And that's just because I created it first. That was the first file I created. And it went, all right, I don't have any other files. This is my top. All I have to do to make add or subtract the actual top file is right click on it and scroll to set as top. And then it sees saying updating. Now add or subtract is the top. There is nothing intrinsically special about it being the top file until you make it so. So the top file is almost always what we would call structural. So a lot of people will rename this from behavioral to structural or just struct. And that's because we're not telling it how to behave. We're just telling it how to connect. Okay, to do that, and I'm going to screw some of this up real quick, I'm certain as we go through, we need to let it know inside of this file that the other components exist. So first off, I'm just going to real quick make those ports, which are going to be A, B, pins. I'm going to call it SD for sum or difference. This no, I'm going to call it sum or diff, just because it's clear what that is. That's an output. If you're using a mouse, the copy and paste thing works a lot better. I'm using a little touchpad, but it can save you a lot of time. And then the last thing that I almost forgot, right, is select an input of just standard logic. Now let's see if I can spot the error. Oh, it's because select is a protected word. So it doesn't like that. That's why I use cell for select. Okay. You'll kind of learn what these errors kind of mean as you go along. Okay, so now I need to start letting it know that these other components exist. So we can go ahead, and I don't want to use my regular mux because it's not equipped to use the vectors. So I'm going to use the mux process. And the way I let it know that it exists is I write, I'm going to make sure I have my notes out on this one so I don't screw it up. Okay, component mux process is ports. I have to tell it what ports exist, right? So it doesn't really know what this component is. So I have to say the component exists. This is how you connect to it. And then I'm going to add the end component right now so that I don't forget to do that and get confused. So the ports that I need from the mux is in here, right? I just need this entity. There's an easy way to do this to make sure you don't screw it up between the component declaration. So that's called declaring the component or the component declaration and its entity. You need to make sure those match. The easy way I like to do is just copy the entity and paste it in here. And then all I have to do is replace the word entity with component and end mux process with end component. 2 changes after a copy and paste. There's no chance I screw that up. That component exists. I now need to do the same thing for the adder and the subtractor. So I'm just going to copy that entity for the adder. Do the same changes, component, and then do the same thing for the subtractor. Okay, all that has done is let the top file know, this add or subtract, that this component exists. These components exist. Now I need to be able to connect them together. To do that, I need to create internal signals to this top file. I do that in this roughly the same location, which is after the architecture, but before the begin of the architecture. So signal, I need A, B. Now this could get confusing, right? Because if I go ahead, actually, I'll finish writing this. A and B, they're standard logic vectors. Okay, this is important because this, oh, because they're ports. Haha, I don't need to do that. So let me doodle real quick so I can show you visually what I'm working towards. So again, we have this concept of the top file. Oh, wait. I called this what? N1, N2 on both of those. This isn't an issue to have multiple ports with the same name. And in fact, the top file has a port A and a port B that are connected to, or are going to be connected to, like so. When I have a port declaration, like here at my entity level, I'm making both a port named A and a signal named A. But I need to give a signal name for, let's say, this node and this node. Because I have a port named sum and a port named diff. But I don't have a signal that connects to them. So this is important, and it's hard for some students to get. There are ports and there are signals. The port is like a plug, something to stick it into. It doesn't go anywhere. You need the power cable to plug into that plug. That's your signal. And its added confusion is that entity creates the port and the signal when you declare the port. So it does. So in order to get the X and Y that I just drew, signal X, signal Y. Okay, now I have those signals that I'm able to use to connect them together. Okay, now I can start telling them how they're connected. But to do this, I need to create what's called an instance of that component. What that means is if I build the adder once, right, I've made that adder. And let's say I wanted 100 of them. I wouldn't have to rewrite code and declare that component 100 times. I would declare the component one time and create multiple instances of that same component. So the way that we declare instances is like so. We first give it the instance name. And let's start with the mux and just call it M1. What I'm using then is that mux process, right? So mux process is now named M1, and it needs a port map. That is saying, where are we mapping these ports to? What are they connected to? And I'm just going to go through and do that for each individual port that I've declared inside of mux process. So I need to take care of A, B, select, and C. So A is just going to A. That's the input. So this is where it gets confusing. So that A on the left is the port name coming in from the entity. The A on the right is the signal name A that is also generated by the port declaration. I end here with a comma, not a semicolon. You can put them all on the same line. I highly recommend don't do that. It makes your code longer, but much easier to read this way. B goes to B. What's next? Select. Select goes to select. And then I called it C. And my output C, so now we're going different. The port inside of the mux, right? The port inside of the mux are A, B, cell, and C. But the net that I'm going to, the signal, is that sum or diff. Does everyone see that? That's the output of that mux that I want. And then I can start doing the same thing for the adder. I'll call add1. Okay, so this is where I start connecting other things together. Well, A goes into N2, B sorry, A goes into N1, B goes into N2, and sum goes out to, I created that X signal, right? Okay, and now we can go like, oh, I made a mistake. I don't want A and B going into my mux. I want X and Y. This is why it's helpful to have those diagrams to tie to your components and your instances, because it helps you visualize those issues, right? Here again, copy and paste is, useful, because rather than add one, it's diff one. Instead of the adder, it's the subtractor. The port map is the same as the A, B, sum goes to diff, right? If you guys ever are not confused where I'm pulling something from, just yell at me so I can catch it. But remember, subtractor has N1, N2, and diff as its ports. So that's all I've done here and mapped them to A, B, and now Y. So the outputs of adder and subtractor, X and Y, are getting plugged into the inputs of this mux process, X and Y. Okay, they're connected now like I want them to be, and the output of the mux is attached to sum or diff. Now I have this larger level module. It's not called top, it's called add or subtract. And all I have to do is send in the values A and B and the select to choose whether I'm adding or subtracting using this module. How do I check if that works? Well, I've got 15 minutes to show you, so let's see if I can pull it off. Now I assume I have a working VHDL code. What I want to do is add a source, but this time I'm going to create a simulation source. I want to simulate it. I generally like to call it whatever I'm testing. So add or sub underscore TB. TB is just abbreviation for test bench. That's what we call our simulation stimulations. So stimulation stimulus is what we're providing, and then we just look at the outputs. Okay, created the file, it's in VHDL, I hit finish. I'm just gonna hit okay like I always have. I'll pull up sources. Now I open up simulation source instead of design source, and I go find this adder sub test bench. The test bench starts out roughly the same way. The test bench does not need any ports. In fact, don't give test benches any ports. I then have to declare what component I'm going to test. Now, when we're testing it, we call it the UUT, unit under test, UUT. So we start off the same kind of way, component. This time I'm testing what we call the high level. So normally we would start off with what we call unit testing, where I would first test the mux, then I would test the adder, then I would test the subtractor, then I would stick them together and do a system test, right? So start with unit, build a system. We don't have unlimited time, so I'm just gonna skip right to system and hope that my adder, subtractor, and mux work right, otherwise we get very confused. Because it's hard to debug all of them at once. It's easy to debug one at a time. Debug is the term that we use for identifying the bug or finding the problem. Okay. So I call the component add or subtract because that's what it's named, is remembering that it's nice and easy to go find its entity and at the very least copy out its ports rather than trying to write them all out by hand and risking a mistake. That component now exists in the mind of the test bench, but it doesn't know how it's wired up. So let's create the test bench. We're going to call that UUT. because we're testing it. It is an add or subtract module. And I again have to do the port mapping. And its ports here, you can actually kind of do the same thing if you really want, where you copy and paste the ports. But it gets kind of confusing for me, so I just like to write them out. So AB select summer diff. A. You'll notice I'm just writing the ports out first. I almost forgot select. There are no ports here, so I have to create signals. There's no ports in a test bench, so you must create test bench signals. Okay, that's easy enough to do. We go to after the begin in the same area. I just say signal. I want an A, a B. They're both standard logic vectors. Oh, the mistake was I did that after the begin. These need to come before the begin. You'll notice if I mouse over that, it's saying A has no actual or default value. That just means I haven't filled it out yet. Now that I've made those signals, they exist. Now, one thing that I would recommend that I didn't do, and I will fill in one just for quick reference as to why, is instead of calling signal A the name of the port, for the purpose of clarity when I run the simulation, I like to add _TB to all of my variables so that I remember that it's a test bench signal. I'm not going to do that so that I can hopefully get this done in the limited time that I have. Now, inside the test bench, I need to create a new process because testing it is always part of a process. The process is what's to do it. So I made the process begin and the end process so I don't forget. And I'm going to create one more thing that's called a constant. I'm going to call it DT. DT, right, being the symbol for the change in time. It's going to be a type of time. So one of the types that we can use is time. We cannot use that in code. We can only use it in simulation. Okay, not in your design modules, but in your simulation, it is fine. And then I can use this : equals to give it a value. It's a constant. It will always be 100 ns or 100 nanoseconds. That's a reasonable amount of time. And then I can start doing things like, let's start with A and B being a specific value. Same way, where I do the : equals, it starts at 0, 0. In VHDL design modules, the initial values don't work. This only works in simulation. The initial values only work in simulation. Reality doesn't work this way. I'm going to do the same thing for the select signal. Select signal is 1 bit, so it gets the apostrophes instead of the quotes. And summer diff does not get initialized to anything because it's an output. I don't want to start the output at something arbitrary. So now I can start giving it stimulation values. I know it starts at zeros. So I can say wait for dt. This is waiting for 100 nanoseconds because I made dt that thing. And then I can start changing values. Let's say A gets assigned to 0, 1. Wait for dt. B gets assigned to 0, 1. What are you angry about? Oh, I'm going to undo my ATB just to be quick here. So this is not exhaustive really, but I'm just kind of cycling through. I now have all of these and I'm going, so select, remember, is 0. So I'm now going to change the select signal. So cell gets assigned to 1. And then I'm going to just step through all of those again. Okay, so I've written my test bench. I've written wait, change, wait, change, wait, change, right? You can actually write this in a for loop if you wanted to, but I'm just going to stick to kind of this brute force method because it's a little bit easier and faster for you guys to grasp. And it works, especially for simple circuits. Okay, so we're changing A's, we're changing B's, we're then changing select and going back through the pattern. Now I can simply run the simulation. It's easiest to do it from over here. Run simulation. If your top file isn't specified correctly at this point, weird things will happen and you're going to be very confused. Oh, look, my simulation failed. And it's going to throw a bunch of errors at me, but I'm just going to go ahead and look at the TCL console. And I'm going to scroll up to this error. Signal cannot be unconstrained. BHD 32. So I found the error. I scroll to the right. It happens in adder. Oops, shoot. On line 32. So I can go to the adder on line 32. It doesn't like this. Well, that's fine. I'm not using it, so I'll just delete it. Sometimes like that, extra code causes you issues. So I'll remove it from the subtractor as well because I suspect it kind of tends to crash at the first error that it sees. So sometimes you have to run it multiple times to get all the way to find all of the errors and fix them. You'll find that just like you saw, the design module didn't think it was a problem until I tried to simulate it. And it was like, whoa, that's not okay. You'll see that a lot. And you'll see some later that when we try and synthesize it, which is make it ready for a real circuit, it'll find other errors even. But once you successfully simulate, you'll see a window like this. You can run for a fixed amount of time by changing that time up here. So let's say we want to run for 300 nanoseconds. So I write 300, choose nanoseconds, and I click this run for, and it'll run another 300 nanoseconds. I can push this button, which zooms to fit. This is your waveform. This is how I start debugging. So I know that if select is 0, so you're seeing how select is 0 to high, it doesn't have a number because it's a bit. It's either low or high. These other ones have numbers. So if I'm 0, I'm supposed to be adding, right? And here, let's look at this time window. A is 1, B is 0, select is 0. So 1 plus 0 is 1. 1 plus 1 is 2. Here, 3 plus 1 is 0. Why did that happen? Why is 3 plus 1 0? Exactly. It spilled over. I lost the biggest bit. Because if I do this, 1, 1 plus 0, 1, I get 1, 0, 0, but I only have 2 bits. And I've just lost the data. So that's actually correct. This is fine. 3 plus 2 is 5. Well, same issue, except for I get 1, right? Let's go look at the subtraction. 1 minus 3 is 2. Well, that's confusing, but that has to do with negative numbers. 3 minus 1 is 2. Okay, that one makes sense, right? Don't worry too much about the subtraction because it can get confusing, but I know that this is working. And you can see it here. 3 minus 1 is 2, 3 minus 2 is 1, 2 minus 2 is 0, right? So this is what your waveform test benches are supposed to look like. Okay, good. And then if you wanted to, let's say that you were like confused about what was happening, you can change what's called the radix by right-clicking on the variable you're interested in, scrolling to radix, and choosing how you want to represent it. Let's say I just want to look at it in binary. Boom. Now I've got the binary there. This is your primary debug tool. This is how you make things. You make the test bench, you make the design files, you make the test bench, you run it and you look at it and compare the inputs to the outputs of what you would expect. There's more to teach, some more useful debug tools, and in the video that I have posted on my YouTube channel, which I'll try and remember to link, it'll cover some of those in detail. I'll get an assignment out hopefully soon that it just involves some simple stuff like this that's more or less recreating what I've just done. And then in not too long, we'll start using VHDL in labs. We're out of time. Thanks for your attention. I do have office hours that you guys can use if you're confused once you start trying this out. I know you guys don't know what you don't know yet because you haven't tried it yet, but hopefully this puts you on the right path for this.
When will be our first time to actually start putting on projects?
I'll make a simple assignment now, and then I have to look at the lab schedule because I'm actually reworking the lab schedule to get you guys using VHDL sooner than you used to. It used to be about halfway through the semester, but by the problem is the final project is really cool, but by the time you get there, you're not really comfortable in VHDL yet. And I want you guys to feel comfortable in VHDL so that you appreciate the final project. So I'm trying to squeeze it in sooner, but I don't know how yet.
So you're not recording like screen recording?
I am screen recording this.
And you also have the.
And I have another one that I designed just specifically for this. You'll have multiple things that you can listen to.
Canvas somewhere, the recording?
This recording?
Yeah.
I'll post it to Canvas, or how do you guys post the closed captions ones?
We typically will do Kaltura, and then we just include a link for the channel.
Is that in Canvas somewhere? Or
yes, we create a module,
okay,
and then it takes you to Kaltura,
okay,
and then it just has all the videos there.
I think normally there's a little tab in Canvas itself that says to have like a calendar.
Yeah, but he doesn't have.
I don't use that. I'm not using that one, but because I'm using the Kaltura one for the closed captioning, and that's what we'll use for the videos.
Okay.
I'll send out an announcement.
Quick question.
Yeah.
Does this like auto save kind of like how Python does every time you simulate it, or?
It does actually, but you can also do Control S, and I just if you don't see it up here, but every time I make a change, I'm just hitting Control S just constantly.